represented here by VBEV. And we're very happy to host you here. And just a couple of organizational things. The restrooms are straight behind you if you need them. And enjoy yourselves. Thanks.
Hi everyone, welcome. So my name's Reynold. Some of you know me before from previous meetups. So unfortunately, Matei himself can't make it today. I just want to introduce sort of the program for tonight. If I figure out how to project this. Okay, just again, special thanks to Clear Story Data and the investor Google Ventures for providing this nice space. And Adam already talked, so tonight is, in the remainder of the tonight, is two more talks. One is sort of take the stage of spotlight tonight with Tachyon, and HY and Ali will cover Tachyon, which is a new distributed in-memory file sharing system. And then I myself would talk briefly, probably 10 to 15 minutes about some updates in Shark. Without further ado, actually, before that, just want to get a show of hands. How many here have heard of Spark? All right, you're not in the wrong room. How many of you started actually using Spark? Wow, it's still get a majority. And how many is looking to just explore and potentially evaluate? Great, I guess that adds up the full set. Okay, without further ado, Ali.
This is the same? Okay, different. Okay. Okay, so I'm Ali Ghodsi. Okay, I should stand here so you can hear me. So my role is more of an advisor to this project together with Jan Stoika, who's in the back. And the main work here was done by Haoyuan, also called HY, who will present most of the details. I'll go through the vision of the project and the high-level idea behind the project before I hand over to HY. And this is, of course, joint work with Matei, Scott, and Jan. But also other people helped out a lot in this project whose names are not up here. In particular, Reynold here, and Kevin, and Dilip. I don't know if you're here. He should be here somewhere. Okay, so let's start. So the outline of the talk is as follows. I'll go through the motivation. Then I hand over to HY, who talks about the system design and some preliminary results that we got evaluating it. And he talks about the alpha status, which is the soft release that we did. And finally, he talks about the future directions of the work. So let's start. So we all know in this room that memory is king. You've all used Spark, so we know that memory is where we want to do stuff. And this is because of two trends. The first one is that RAM throughput is increasing exponentially. So this graph here shows that on the x-axis is the different years, and y-axis shows gigabytes per second. And what we see is that the increase is exponential. And if you look at 2013, you're getting roughly 40 gigabytes per second on a quad channel these days. If we, however, look at disk speed, we see that the throughput is increasing much slower. So you get this kind of log shape. And in 2013, you're getting maybe, at best, 150 megabytes per second from disk. So this means that memory locality is key to achieving interactive queries and fast query response times, which is what I think most of us in this room are interested in. And this has been observed by many. So if you look at the current big data ecosystem today, already many frameworks are exploiting memory. So many things are stored in memory. You've already heard of Spark and Shark, but there are also other projects like commercial databases out there that are all in memory stored. So that's already something that many people are leveraging. However, file sharing between different jobs is currently replicated to disks. So by jobs here, I mean it could be different Spark jobs, but it could also be that you have a MapReduce job that puts its output to disk, a Spark job reads that, does further computation, puts it to disk again, and then maybe Storm picks it up and does some stream processing. Okay? But in all these cases, it goes to disk and it's replicated. And the reason it's replicated is that this replication enables fault tolerance. So if one of the disks goes down, or a machine goes down, you can still get it from another replica. So you might have 3 replicas in your data center. Okay? So the problem is, as more and more of these frameworks start exploiting memory like Spark does, the main bottleneck will become this disk replication, replicating this data for fault tolerance. So this is the main problem that we wanted to attack in the Tachyon project. So this was the sort of start of the project. And the Tachyon project, what it does is that it provides reliable file sharing at memory speed across different frameworks like Spark or Storm or Shark. And it does so at memory speed. So we want every operation reads and writes to this file system to go at memory speed, but we want it to be reliable at the same time. So that brings up the following challenge, which is how do we achieve this reliability without replicating? Remember, we did replication, or existing file systems do replication so that they can get fault tolerance, but that slows things down, but we want to be at memory speed. So how do we solve this? So the main idea behind Tachyon, which it actually borrows from Spark, so it should be familiar to many of you, is that it keeps track of the lineage of the files on the file system. So it has metadata, and it also keeps track of the binaries that actually generated the files. So it has these jobs, so it knows how to actually recreate files that are missing. Okay? So given that it has this lineage information, it can get away by just keeping 1 copy of the data in memory. By keeping 1 copy in memory, it can completely avoid replication, and all operations, all reads, writes can go at memory speed. Okay? So that way you get both high throughput and reliability at the same time. So what Tachyon really provides is that it comes with the integrated workflow manager. This workflow manager knows actually the workflow of jobs. It knows the binaries, it knows their metadata, it knows how to re-execute them, and it can launch jobs to recompute the data. And we think that this is kind of exciting because you're sort of lumping together, or you're solving 2 problems at the same time. You're solving recomputation and scheduling of jobs and file system, and keeping track of files and serving them efficiently. You're solving them within 1 system, and we think that provides a lot of opportunity for optimizations. Okay, so what does that mean for a project like Spark and Shark, which are our main users currently? So the main benefits that a project like Shark or Spark gets is that you get memory throughput file sharing between different jobs. So currently, if you run 2 different Spark jobs, you would have to go to disk. You would maybe go to HDFS. But with Tachyon, you share it through Tachyon at memory speed, and you can do so reliably. The second thing you get is fault isolation. So should a JVM that is running a Spark job crash, or if you want to restart it, you're not going to lose all the memory and all the RDDs that it keeps. But you can actually, that's external in the Tachyon system. So this is the high-level vision of the project and the main ideas behind it. So I'm going to hand over to HY, who will talk more about the architecture and the design.
Hello, I'm HY. So Li gave a very good introduction to the motivation of the project and also the initial test to the system. So I'm going to go more about the details. So this picture shows where Tachyon sits in the current stack. Say it's Tachyon in-memory file system. It sits between the computation frameworks such as Spark or MapReduce and on top of the existing distributed file systems. And this is the architecture of the system. It has a single master, and workers running on every single node, they will manage the data on nodes. So the master tracks the status of every worker node and the location of each file. And on each worker node, there is a worker daemon managing the node and reporting its status to the master. And then each worker node also runs a Linux ramfs, which managed by the worker daemon and store the real in-memory data. And there's a client library used by framework applications, and they can talk to the ramfs directly to access the data to achieve the full memory speed. So this architecture make the read as memory throughput. And for the write, like Ali mentioned, like Spark relies on RDD, and we use the lineage concept to achieve this. And this graph shows the basic example of a lineage. Basically, suppose you have dataset X, and you have a Spark program, and this program read X and generate Y, and you have another MapReduce program read Y and generate Z. And then if we can record this information reliably somewhere, and then later on, if Y or Z got lost, we can just relaunch the program to regen the data. And Tachyon just preserve this information to make this fault tolerant. And here we have two assumptions. The first one is all the data set itself, they are immutable. And the second one is the program itself is deterministic. And therefore, the write is not blocked by the replication anymore, and they can achieve the memory speed by keeping a single copy of the data in memory. And here, so in order to capture the lineage information, from a high level, the following information is required. We need the binary program and its configuration, how to run this program. And then we also need the input file list as well as the output file list. Therefore, we know like if a file got lost, we know which program to run to regen the data. And we also need to know that which files it depends on. In case this file also missing, we need to regen it too. And also, the dependency type is also useful. For example, it tells you whether this is narrow dependency or wide dependency. By knowing it's a narrow dependency, you can therefore, Tachyon can therefore initiate a more efficient data recovery for any lost partial data. And Tachyon provides this API to allow frameworks to submit this information. And we have implemented a 200 lines patch for Spark and a 200 lines patch for MapReduce to make the recommutation-based fault tolerance working with Tachyon. And also, one thing worth mentioning here is this API only needs to be exposed to framework programmers, but not like application programmers. All the applications running on top of those frameworks, which supporting Tachyon, should be able to use this feature transparently. And those application programmers doesn't need to know this details stuff. Okay, so since Tachyon uses recommutation to achieve fault tolerant, it needs to, if the failure happens very often, obviously maybe the overhead of regenerating this data may be higher than the benefit the memory speed the memory read or write can get for you. But the good news is the node failure is not that often comparatively. So based on a report from Yahoo HDFS paper, there are only 1 or 2 nodes failure every day for a cluster with 3,500 nodes. However, when failure does happen, if the data generation takes a long time, data regeneration may take a long time if the lineage is deep. So here is an example. Suppose you have an input data set and you have program A, B, C, and D, and they all read the output of the previous program and generate final output, which is an output data set. And that's the thing we want to get. And after all this computation has done, one node got failed. And part of the dataset 1, 2, 3, and part of the outside dataset got lost. Then we need to regenerate, rerun this one A, B, C, and D. They could be time consuming. So how we are going to solve this is we use asynchronous checkpointing, like to checkpoint the data asynchronously while they were generating. So for example, in this case, if we have checkpointed dataset 2, if any data from outside output dataset got lost, we only need to rerun C and D inside of rerun B, C, D. And in our prototype, we implement the algorithm to have a bounded recovery time in any case. And in our report, we also show that by using Tachyon, even under failure, the performance should be much better than existing solution, file system solution. And the other point we want to mention again is the failure is relatively rare in many cases. Okay, so we have implemented the system in Java plus Maven and Thrift, and this is a read performance. For this benchmark, we run Spark on top of Tachyon or HDFS to read the data on a 40 EC2 nodes cluster. And as you can see, the detailed setup is on every single node, the Spark program will read 42 gigabytes of data. And then you can see on the left side of the graph is HDFS performance. It's around 4.5 gigabytes per second overall overall of the whole cluster. And on the right side is Tachyon. It's almost 1 terabytes per second. And in the middle, the second column is the flight data center storage from reported performance from Microsoft. And the third column is the theoretical maximum disk bandwidth, if you assume it's a 3-way replication, and each single node has 12 disks. And this has been done in our preview release by using our native API. And this is what we have done in our prototype. So basically, we have a similar setup using 40 nodes. And on every single node, we do Spark task to write 42 gigabytes data. And you can see that on the left side, HDFS has around 1 gigabytes per second because of a network or a lot of other overhead, such as disk contention. And for Tachyon, it's a little bit more than 300 gigabytes per second. And we also run a simulated workflow using Spark, which contains around 400 Spark jobs. And on the left, this graph shows what's the end-to-end latency for this all 400 jobs. And on the left side, the Tachyon performance is around 2.5 minutes. On the right side is the it's maybe 40 minutes something. And the speed up is around 15 times. But we want to point out that this really depends on the workload. But suppose if you are very CPU intensive, this will not have this much. And we also got some real workload from Conviva. And one is a simple, this one is a simple Spark query, which is very I/O intensive. And in this case, we run in 3 different settings. The first one is we run Spark job on top of Tachyon, and we measure the overall latency. And the second is we run a Spark job and read the data into the Spark cache, and then we measure in the deserialized format, and then we measure what's the execution time only. And the last one is we run the job against HDFS, which is the current production setting. And the x-axis is the data size, and the y-axis is the end-to-end latency in terms of seconds. It's in the log scale. As you can see, as you can imagine that both Tachyon and Spark cache outperforms HDFS a lot. It's more than 75 times. And at the beginning of execution, Tachyon and Spark cache, they performs almost identical. But in the end, the interesting thing is Tachyon can outperform Spark cache in this case. And the reason is when you have a lot of data in Spark JVM memory, that will trigger more often GC when the memory limit is trying to approaching the JVM like maximum memory you configured. In this case, since in Tachyon case you put most data inside of Tachyon, not in Spark, there's no like garbage collection in this program in this run. So Tachyon outperforms Spark cache in this case. And we run another Conviva Spark query, which is less I/O intensive and contains several data shuffle stages. In this case, we only outperforms HDFS on 12x. And the other thing is garbage collection for Spark cache case kicks in earlier because for this more computation intensive job, they use more memory for their own state keeping. Okay, let's talk about our release status. We had 2 developer release last month, our version 0.2.0 and 0.2.1. And this developer preview release is the first step in our approach. Say, for the first read of the file, it will be cached in memory, and the write will go synchronously to HDFS or any underlayer file system. So no lineage information is kept in this developer preview release. And Spark, one interesting thing is Spark and MapReduce, they can run on top of this without any code change. And what you will probably see is when you run these jobs on top of Tachyon, the CPU utilization will be approaching like 100% if you have enough tasks running on the node. And probably serialization and deserialization will become the new bottleneck. And in order to use this for Spark, say previously when you create RDD, you say data equals to Spark context.txt file, and you gave the HDFS URI, and now you only need to change it to be a Tachyon URI. That's it. Then you can use Tachyon. And in the current release, this is the features we have. Our native API is a Java file-like API, and we also implement a Hadoop file system interface, and to work with any existing Hadoop file input format or output format. And thanks to Mark from ClearStory, we can compile both with Hadoop 1 and Hadoop 2. And we also have native support for raw tables. It means that in a data warehouse workload, you have a table, right? So in the table, it has a lot of columns. Some columns may be queried quite often, and some will never be queried. Therefore, in our case, we separate them into column base, and we can only keep the hot column in memory and leave out the cold columns. And we also have a pluggable underlayer file system interface. That means that you can plug any existing distributed file system you want to use under Tachyon if you implement this interface. For now, we only support HDFS and a single node file system, but it's not that hard to implement others. And someone is trying to work on Ceph to make it also work with this Tachyon. And we also have a command line interact. You can also use command line to interact with the system. And the other thing is we have a user interface, which Kevin made, which is pretty good, we think. And we also support two features called whitelist and pinlist. The point is for the whitelist, when you try to read a file right from HDFS, only the file's name can pass the whitelist, which is a prefix list check. Then Tachyon will try to cache it in memory. For the pin list, for anything past that check, they will be pinned in memory unless you unpin it later. And as I said in the beginning, in order to take the full advantage of Tachyon, you require a close integration with it. So for the first step, we had a close integration with Shark. And the next Shark release can store Shark table in Tachyon by using a fast columnar serialization, deserialization. And these are some numbers for some simple queries. The first one is a full table scan. This will basically read the whole table. And for Spark cache case, it took 1.4 seconds, and Tachyon to 1.5 seconds. And it's like less than 10% overhead here. But then we run some group by queries from TCPH benchmark. If you set this Spark memory size to be 10 gigabytes, the Spark cache will take 50 to 90 seconds to run this query because of the garbage collection. And in Tachyon, as we said, most data will be kept in Tachyon. So in this case, Shark doesn't have that often garbage collection. It only takes 45 to 50 seconds. And if you increase the Shark memory to be 15 gigabytes here, the Spark cache performance improved to be 44 to 48 seconds, and the Tachyon case improved to be 37 to 45. And my colleague Reynold will talk more about this in his talk later. And here is the UI we have. Let's try to click this. Oh, we got it. We got here. Yeah, this is the UI. Oops, no. Okay, let's move this. You don't need to move that. Yeah, let me move this. Yeah. Oops. Yeah, we have it here. So this is the Tachyon UI. As you can see on this left side is the Tachyon cluster version number, and when you started, it's been running for more than 2 weeks. And the right side is a cluster summary, like how much memory do you have in total, and how much memory you have used, and how many workers are running here. And this is a pin list. And this is the whitelist, which is a slash, represent anything, any file will be cached if they are read for the first time. And then this is a detailed node summary, and you can click this, yeah. And you can also browse the file system. Say, for example, you go into this, and these are some data. If the data is in ASCII format encoding, you can just click it, and you see some content here for the first 5 kilobytes. Yeah. Let's move this back. Oops. Okay. And then we have another page for this. Since we have seen this, let's move on. And AmpLab is also putting effort to make our software try to be production ready. And Matt is the lead effort on this. And Tachyon has been integrated with our Jenkins testing infrastructure. So for every commit in the GitHub, it will be compiled automatically by Jenkins and run all the unit tests on this. And we can also click here. And yeah. And this is a Tachyon compile with Hadoop 1. This is compiled with Hadoop 2. And you click into this. You can see what's the test coverage. We try to improve the unit test coverage. This one. Yeah. Okay. Okay, and then we come to our short-term roadmap. In the short term, we are going to improve the current implementation first, which including try to enhance unit tests and enrich the code documentation and the wiki. And we're also going to enhance our HDFS file system interface implementation. And as you can see, it's a single master architecture. We're trying to make the master fault tolerant and try to provide efficient SERDI as the next step. And we also try to make benchmarks for different components' performance for long-term development. After this, we are trying to add the lineage back into the system. And here's the more information about if you want to know more about Tachyon. The first link is our homepage and our GitHub repo and a wiki. If you want to try Tachyon locally, you can go to this link. And you probably can run Tachyon within 5 minutes. Yeah, that's it. Thank you. Yeah, sure. Yes, you're asking what happens if memory is not enough. Yeah, so basically now we have an LRU mechanism to spill out the data. And we also make this particular component pluggable. Therefore, anyone can implement whatever policy most works best for them.
And also, can you bound the amount of memory it uses?
Bound the memory what?
The amount of memory it uses.
Yeah, sure. So basically, from the let me see, from the our UI. From our UI, you will see that what's the total capacity. So we'll make sure no node will exceed this capacity for every single node.
But is there a configuration where you can change it?
I'm sorry?
Configuration.
Yeah, it's configurable, yeah.
So how does the memory for Spark compete with memory for Tachyon? I mean, like, it's all the same memory, right? So if you want to increase the Spark cache, you have to decrease the Tachyon RAM. And how do you now make decisions? So I understand you basically instead of caching, Spark you just don't cache it, right? You assume it's all went from disk from the Spark point of view. So how do you make these kind of decisions? How to split the memory?
So you're asking, say, you run a Spark program, therefore it uses memory, and you also need to assign memory to Tachyon. How do you make the balance, right? Yeah, so this is a very good question. So we don't have a definite answer here, but in general, say, suppose if you only have one Spark program in the system forever running there, you can just assign all the memory to Spark, right? But if you have different Spark programs that share the same input data, probably you want to have the Tachyon to at least keep those data. Yeah. But yeah.
Follow up. So I mean, previously I knew Spark is my personal computer. If I'm using the memory, nobody else can use it, right? Because I have all of my data sets logging all the memory. Can I now use Tachyon as a way to share among other users?
Yeah, that's the point. Yeah, so you want to use Tachyon to share the data across different jobs, across different frameworks. Yep.
It sounds like Tachyon is pretty similar to, or giving you a pretty similar effect as memory map files. And have you benchmarked the difference? Wouldn't the difference be almost inconsequential?
So basically, on every single node, as I pointed out, there is a RAMFS running on every single node, and we have native API. Our native API is Java-like file API. It provides input stream and output stream as normal streaming interface, and also we provide the memory map I/O. That's the thing as you mentioned. So we just use memory map I/O to achieve the best performance.
It seems like you could skip the serialization and deserialization that you mentioned with bottleneck and just go straight to a native Linux memory map file and have less overhead. So I don't understand.
Yes.
What's this doing for you other than slowing it down?
So one thing that, I mean, I don't know if this is being recorded, but the whole idea here is that you can recompute upon failure, right?
Oh, yeah.
So if things cannot fit in memory, or some file is missing, or if there's some machine that crashes, Tachyon's main task, I mean, that was the essential idea, right? That we keep lineage information and we can recompute. If you just do memory map I/O, you don't have that. So that's what Tachyon does.
Okay, and
In addition,
Let me add something else.
Yeah.
So then I think one thing it is true. So Tachyon actually uses memory map I/O on each individual node. And think of it as a layer that's sitting on top of each of the individual nodes and connects it all together to expose a single coherent file system.
So that means that the fabric, your switch fabric, or whatever you're using to interconnect becomes a determining factor. There was no mention of what you're using to interconnect your nodes. Could you say
Yeah,
about
yeah.
that?
So as I understanding, you have two questions. The one is why serialization and deserialization could become the next bottleneck, right? Since you are using memory map I/O. The other thing is since everything on single node is memory based, so the network may become the next bottleneck. That's our two questions, right? So for the first one, if you use like C or C++, you can do memory map and you can map the memory directly into the structure. Therefore, you don't need to do serialization, deserialization. But in Java, depends on how you encode the data. Sometimes the serialization, deserialization could be very expensive. That's the reason why I mentioned that could be a bottleneck. We're not saying it's absolutely the bottleneck for any cases, for every case, but in some cases they become bottleneck, especially for Java-based applications.
and also we want to enable across different frameworks, right? So you might have Impala written in C, and you want to share data between that and Spark, which is in Java. So you can't avoid the serialization that easily.
For the second question you have, whether the network become the bottleneck, this really depends on the workload. If you have workload, say, you don't have much like shuffle or much network traffic, so in that case, you don't have that bottleneck. But you have maybe have graph computation, where you have a lot of network I/O, network traffic that will become the bottleneck.
Are you assuming using 10 gig interfaces?
We don't assume that you use anything, but for some workload you don't have that much like traffic, right? So
You're still scheduled for locality.
yeah, that's
Your schedule has for locality, and let's say you launch a MapReduce job, so map still scheduled to where the data is. So it does memory map I/O on each of the nodes.
yeah. Those frameworks will try to take advantage of data locality whenever they can.
So how is the data of a data set transferred from one node's memory to another node? Does it happen over network, or do you just read it from the second node from disk and just read on the whole image?
Oh, I see. You're asking what about the remote read?
Right.
Yeah,
If I have two jobs running on two different nodes,
I see.
the same data.
They want to read the same data, but data is only in one memory, right? So for now, if the data is already for the current implementation, if this data is already in one machine's memory, the other job will fetch from this. The worker will be responsible to send it to the other node and to answer the other node's request to get the data. But this is really a policy issue. We can also do, say, if this particular node try to read the data, but the data is not on this particular node's memory, you can say, I want to read from the whatever remote or local disk. So this is policy based. We can do. I didn't see any. We probably can do both. It depends on which one do you want. I didn't catch the first part of the sentence. Say again. Sorry.
Yeah, it's a big cluster, right?
Yes.
Nodes in there. So if you really want to share data over the network from one node to another, right? Then, for example, you can have n squared number of connections. So scaling of number of connections will be really big problem there. So I thought, okay, are you just really going over network or through this?
I agree. That's a good question, and this exists in like any distributed file system, including like HDFS, and that.
Okay, that problem is not tackled. So
Yeah.
So if your data happens to be on HDFS on the same node where you're trying to read it, is it possible to do sort of a zero copy read and skip user space completely by utilizing the fact that it's on the same node?
So are you asking the data is already on the same node disk and?
Yeah, I mean, so for example, is it possible to do a tight integration with HDFS to be able to move data from disk directly to RAM disk without skipping going through Java?
Oh, I see. That's really depends on whether HDFS provide this feature or not. If HDFS allow us to get the data directly from the disk without going through the Java code path, that's possible. But it's not depending on this Tachyon layer. Did I answer your question?
Yeah, I mean, like, are there hooks in Tachyon to be able to do such integration eventually?
Yeah, I didn't see any obstacle from Tachyon side to use this if this is provided by other file system.
Your master is still single point failure.
Yes.
So it looks like you haven't learned from HDFS. A lot of people are facing problems with single point failure and everything. So you're not addressing right now.
Yeah, I agree. That's the reason why in the short-term roadmap we try to make it fault tolerant.
And one more question.
Yep, sure.
The map reduce, like I don't know what Spark map reduce, but like does it know the where the data is so that it can schedule the task on the worker node? Does it know?
I didn't hear it.
Tracker, for example, in Hadoop.
I'm sorry. Can you say it again? I didn't hear it.
And regular Hadoop, job tracker knows where the data is and it tries to move the function.
Oh yeah. Yeah, Spark also provides the data location to the upper layer frameworks. Yeah.
Tachyon.
Cool.
That's part.
Oh, Tachyon. Yes. Cool. Thank you.
All right, you guys could corner him. All right, thanks HY and Ali for introducing Tachyon, and you guys could corner them afterwards. So just to give you a quick update, it's going to be a short presentation about Shark and the upcoming plans, and some of them are covers actually both Shark and Spark. And before I do that, I just want to go back in history and look at what happened in the last sort of year. So about a year ago, we released the very first version of Shark, and Cliff here. Cliff, can you put up your hand? So Cliff, who used to be at UC Berkeley, actually wrote the very first version of Shark. And since then, he joined Google. So we released a 0.1 version, and in 0.1 version works with, I think, Spark 0.5. I don't remember, it might be wrong, but it's based as far as I can recollect. And we released 0.2 in October, which improved much better of the Hive's compatibility in November, and that supports Spark 0.6. And then at some point, a month later, we released Shark 0.2.1, which works with Spark 0.6.1. And then a sort of a dead silence with the version 0.3 sitting on the master. And no one knows what version it really works, what kind of Spark version it works with. Sometimes get questions on a mailing list. People ask, so we have this thing, it doesn't work. It's just hanging there and we took a look at the reason because there's a Spark compatibility problem. It's using a different version of Spark to talk to another version of Spark. And then we heard enough complaints, so we're actually doing some changes here with the release versioning. One is we're going to move to a faster release schedule, and the other one is just I think we reduce the degree of confusion. Is we'll synchronize the Spark and Shark versions. So Spark 0.7 will work with Shark 0.7, and Spark 0.8 will work with Shark 0.8. And this is actually probably the next 2 release schedule. Spark 0.7 will come anytime now. It's blocking on the very tiny little thing. And then Spark 0.8 will release later this summer, and along with the Shark 0.8. So seeing the remaining of the talk, I'm going to talk about the improvements we have done in Spark Shark 0.7, which is the next release. In particular, I want to highlight the Tachyon integration, since tonight's Tachyon's night. And then I'll talk about the rest of the improvements in 0.7, and then some of the future stuff we have planned in 0.8 or further. So to talk about the Shark Tachyon integration, let's look at how Shark works today. You have a Shark Shark as a user level program sits on top of Spark. And Spark really provides an execution engine as well as a in-memory storage engine to Shark. You could have multiple users connecting as JDBC clients to the Shark server, a Shark instance. And then they all talk to the same Spark cluster, caching data in memory in the Spark cluster's block manager. This means you have a couple storage layer and an execution layer. So what happens is you have users running, and we allow UDFs, and you could run some crazy UDFs, which actually crashes the cluster. And what happens if you crash Shark? Of course, everyone else lost their connection because you actually crashed the whole cluster. And then next is, you not only do you crash Shark, you also crash the Spark because they're actually sitting in the same process, the execution engine, which means you actually lose the block manager, which is the storage layer. And now, say you want to provide higher isolation. I have let's say my department A has my dedicated Shark cluster, and department B has a dedicated Shark cluster. We're not going to interfere. But what's going to happen here is it ended up actually duplicating all the blocks in memory, because Shark cluster 1 can talk to Shark cluster 2 to fetch data from the heap. And that comes to Tachyon, which is once. So this with Shark will be within 0.7 with Tachyon deploy. So Tachyon provides an extra layer of storage, in-memory storage that's sitting beneath Spark and Shark. So you have an execution engine. They can read directly the data cached in Tachyon in memory. And multiple instances of Shark or Spark can actually access the same set of blocks in memory. So have a single copy of everything for much efficient storage. And which means no duplication. And then if your Shark instances crashes in one of them, the other one still works. You can still read the same set of data in memory from Tachyon. And even better, the second one, the one that just crashed, could actually recover instantly without rebuilding all the data in memory, because those data are just sitting in memory, and crashing one of the JVM processes is not going to affect any of the data that's already in the RAM disk in Tachyon. So this is introducing the Shark with Tachyon integration. It's actually so most of the work are done under the hood, and exposing to the user is very similar to what we had before. Basically, you could create a Shark in-memory table just using the create table statement, similar to how we do it for on this data in Hive. You could do create table, the table name, And you could specify the table property to call Shark cache. And if you assign it to be Tachyon, it's going to put the data in Tachyon in memory. It still works with the Spark block manager or Spark heap. You could still say Shark.cache equals heap or Spark or anything else other than Tachyon would go to the Spark heap. And then you could, one sort of misconception about this Shark cache storage is a lot of people think it's just a dumb caching layer, taking, you cache the data on disk and put them in memory for some blocks. But you could actually select optionally doing any arbitrary filters or aggregations to build up actually in-memory table for after some computation. And then you could only put those data of interest in memory rather than all the raw data on disk. And just to recap the benefits once you integrate with Tachyon, one is you could actually share this data in memory across multiple instances of Spark and Shark and potentially even other frameworks. And the second one is you get instant recovery if your cluster crashes. You basically just reboot the cluster. Takes like probably a second or two. And the other benefit, which HY mentioned in his talk, is you get actually much faster GC because your heap is a lot smaller. When you're dealing with big data and you're starting to see memory the nodes memory getting anywhere to 500 gigabytes. The largest I've seen, the largest I've used actually is a terabyte of RAM on a single node. And if you try to scale the JVM heap to a terabyte, God bless you. So this has been brought up once already. Isn't it slow for the JVM programs to read and deserialize data to the format that JVM actually understands when data are off heap? So we did a couple of clever things. One is HY sort briefly alluded to the raw table API in Tachyon. So what that means is actually Shark can store each of the column on a partition. So first, tables are partitioned onto each node. And on each of the partition, each column is a single file in the RAM disk. And then we use exactly Java NIO to memory map the file into the JVM. And then we use this thing called unsafe to do direct byte buffer reads. And unsafe, you haven't heard of it, I highly encourage you to give it a shot. It's actually pretty safe, other than the fact it might crash your JVM. But if you use it carefully, you'll be fine. If you don't write, remember the days when you get a sec fault in C? That's what happens if you write unsafe programs incorrectly. But what it gives you is a very powerful way to read arbitrary memory address and read an int, read a byte, or read a short, or even read a direct memory block. And we actually use that together with the memory map files, which means you do 0 copy of the memory data, and you have very fast reads, C-style reads from those. This is just, if you're curious, unsafe actually has a private constructor in Java that you can't even invoke. The only way to do it is you have to use reflection to get unsafe. But it's pretty fun. You can poke around the Shark source code right now on GitHub to see how we use it. So that's the Tachyon integration. And the second part of the talk is on what are we bringing to Shark 0.7 other than the Tachyon integration. So it's actually numerous features and bug fixes, but I'm just highlighting some of them here. One is a much improved EMR and EC2 and S3 support. So now you always could run queries on data on S3 without importing them. But now you could even run queries files that are specified sitting in S3. So this is actually someone posted on the Melon just, I think maybe 2 evenings ago. And look, it was really simple to implement. Basically, we just open a connection to S3, read the file streaming, and execute it. So this is, if you have, let's say, workloads, a dedicated workflow that's already set up, and everything's stored in S3, you don't even just create local copies of anything anymore. And even better, Shark will pick up the AWS credentials directly from environmental variables. And then there's added data types. There's both timestamp and binary. There's an Avro SERD that supports Avro input formats. And then clear story there. This is actually a pull request that hasn't been merged yet. We Mavenize Shark, so moving to Maven build. and then there's DBM packages, which for easier deployment. And there's a couple other things. One is Shark had this SQL to RDD API. What it allows you to do is you could execute a SQL query, but instead of returning a result by materializing them in the master or the driver program's memory, you actually returns an RDD in Spark. And then you could do arbitrary RDD operations on that result RDD. So we improved that. And it used to be an experimental feature, meaning it was the one quick program I wrote, maybe on a weekend, and there was no test covering it. So now we actually change all the Shark programs test suite to use the SQL to RDD API to test all the SQL features. So this is actually now fundamental to our own testing, which means it's one of the most tested feature. Went from experimental to the most tested feature in Shark. Feature-wise, what this allows you is you could integrate, have a very tight integration of Spark and Shark. For example, you could use Shark to select data of interest from a data warehouse, and then without moving data anywhere, you directly run Spark programs, like, for example, if you have a k-means program to do clustering on that. And then there's a minor thing about limit zero support. There's a lot of BI tools, especially Tableau, use a select statement with a limit zero to test whether a table exists or not. And this could waste a lot of cluster resource. So now if we see a limit zero, and if the table exists, we just returns true, returns nothing, and then without any errors. And then there's a new contribution map joined from Yahoo. That's and you could also now insert more data into a in-memory table. So this basically allows you to update table. We don't support deleting data yet. That's coming up next. And there's multiple bug fixes. I somehow had this clear story here because they've done a lot of, they fixed some annoying bugs in Hive. And I think this is the last slide, which is just some of the improvements we have planned. And the only thing I included in this slide is stuff that I've seen either a pull request or I've seen prototype implementations. So I think I'm pretty confident almost all of them, if not all, will make it into the point A release of Spark and Shark. One of them is the fair scheduler implementation, that if you have a single Shark server, which allows multiple clients to connect to, right now there's a 5-fold order of execution for concurrent queries. And there's a fair scheduler pull request now sitting on Spark that will basically support fair scheduling among multiple clients. And then there's another shelf big patch from Intel coming in on improving performance on when you have a lot of cores. And you can probably figure out why they want that. And then the next one is actually Patrick and I have been working on a performance improvement when you have a large cardinality aggregations or joins. That code is actually mostly ready, sitting on some GitHub branch. But we just need more time to do testing. And then this work about the compiling expression evaluations down to bytecodes that Yahoo started, and now it's actually taken over by Intel. I think we'll see a patch coming very, very soon. And the other thing is we actually talk about now you can insert data into memory. You can't remove it yet. You can add more data, but you can't delete. So that's the other thing. We already laid down the foundation in Spark to do unpersist over on RDD, so you can get rid of RDD in memory. So we just need to hook up Shark to that. And last but not least, in-memory data compression, which is memory is precious. We want to dump as much as possible into it with very CPU efficient compression. And hopefully Nandu sitting there will take care of that. So that's all I have, and I think that concludes tonight's presentation part. A lot of us will be here, and you feel free to corner them. And one thing is we are actually looking for future meetup locations. If you have a space that's like this or even bigger, it would be even better. Please talk to us. Thanks. Or any questions, I guess, quick ones. Yes?
You mentioned about multiple Shark instances sharing memory with Shark tasks still need to serialize the data into their own heap, so you do end up duplicating if there are multiple tasks running on the same Tachyon node, right?
No. So so Shark follows an iterator-based model, which means you stream through the data. You basically fetch like say one record at a time. So you duplicate like one record at a time. And it's not even duplication. It's really the internal representation of the Shark row is really just a pointer to the memory address in Tachyon for the files.
But at the point when they deserialize it, then they would be.
Let's say you get an int back. You don't copy the whole block. It's basically streams through. Yes. One way to do it is, I mean, you could, okay, the question is, right now there's no way to remove it. There's one way, which is you could kill a cluster. So that kills all the files. Currently, that's the only way. If in Tachyon, you could actually delete the file in Tachyon, right? So if you put it, there's no way for you to remove files if they're on Spark heap right now, other than killing the heap itself. All right. Okay, I guess two more. Go ahead.
Yeah, the share scheduler and some of these other improvements, do these also exist in the Spark layer?
Yeah. So it is actually so Spark takes care of a scheduling, task scheduling for Shark. So that's actually a Spark layer thing. Yeah. Mikhail, last one.
Is there a columnar representation for Shark data in memory right now, or is it still row by row?
It's columnar from in-memory data.
So if that exists, is there a plan to optimize operations on vector?
Oh, like vectorize? Possibly. It's one thing we haven't looked into yet, but I think it actually wouldn't be too hard to do some degree of vectorized computation. Especially, even better, you might even be able to do like GPU computations. I think it would be a fun hacking project if someone wants to do it. We might tackle it eventually ourselves at some point too. Yeah. Okay. Well, so feel free to welcome and have fun, mingle, and talk to us. Thanks for coming. Sure. I don't have their file, so. Oh, you have his. Okay. Oh. Okay, but we got most of it. Nice. All right, that's good enough. That's hi, hey. Oh, hi. Yes.
Cool. Did you guys experience like agents like play with the